If something is not reliable, we can't depend on it. We can't make plans based on its use. We dare not make judgments based on the information it provides. If we try, errors are likely to occur. Reliability is a standard we used to judge the usefulness of something. This is true whether the thing is a machine, a person, or a test. If we are late, we are considered unreliable and undependable. Clocks that don't provide accurate time and cars that won't run are examples of things that do not meet our expectations. These are things we cannot put confidence in. Tests that will not measure consistently are not worthy of confidence. When we measure physical attributes, measurement can be precise and reliability is usually high. The measurement of psychological attributes is seldom exact. A certain amount of error is always present. This is true of virtually every test which is used to assess individual differences. It is true of ability, achievement, interest, aptitude, and personality. As long as the mismeasurement is not too great, the test can continue to serve a useful purpose. But if the errors occur often or become too large, the usefulness of the test is limited. When a test measures erratically, how do we know if a score is right, wrong, or even close? If we can't be sure an obtained score is reasonably close to a true score, how do we dare use the test results? When there is more than one assessment tool available to measure a particular trait, there are 4 items we need to make sure are considered. First, suitability of purpose. Second, suitability for the person. Third, reliability of the test. And fourth, validity of the test. This video deals with the third term, reliability. The other 3 items are not topics of discussion for this module. However, the 4 items are not mutually exclusive and, as shall be seen, intertwine in several important ways.
When we refer to reliability, we are referring to the property of a test to measure consistently and dependably. Reliability is concerned with 2 questions. First, does the test measure consistently? And second, if the test doesn't measure consistently, what causes that inconsistency? When we speak of reliability, we ask the question, if I give this test a second time, what is the likelihood that the scores on the second administration of the test will be nearly the same as the scores on the first administration of the test? There can be many reasons why scores on 2 administrations of the same test will differ. First, there are differences in testing conditions. For example, the temperature of the room may change from one situation to another. The lighting may be different. Or we may relate to one test administrator better than to another. The timing may also change. Second, learning which occurs between the 2 administrations of the test. If I learn something between the 2 administrations of the test, it will affect my second score. Third, situations which cause our attention span to change, such as a family emergency, a change of medical condition, or something which produces anxiety. These are only some of the many reasons why test scores on 2 administrations of a test may differ.
Consistency is the traditional concern of reliability, but when assessing persons with disabilities, causes of inconsistency are also of concern. When testing persons with disabilities, it is sometimes necessary to modify testing conditions. Some modifications may affect scores very little. Other modifications may have considerable impact on scores. This may vary from test to test. For example, some test scores may be greatly affected by allowing extra time. The scores on other tests may be affected very little by allowing extra time. When we change the conditions under which a test is used, we may also change the test reliability, scores obtained, and interpretation of the results. Both the WISC-3 and WASAR intelligence tests include picture arrangement as a timed subtest. The WISC-3 cards for picture arrangement are on heavy tagboard. These cards are easy for persons with motor control problems to manipulate. The WASAR picture arrangement cards are on much thinner cardstock. These cards are much harder for a person with motor control problems to manipulate. Would it be permissible to mount the WASAR cards on thick tagboard to make them easier to manipulate? How much would doing this affect scores? Would this modification affect the ability to compare the performance of the person with disabilities with the normative sample? Would not making this modification make the results even less comparable? When modifications such as these are made, what adjustments to interpretation are necessary? When the causes of test score inconsistency are understood, questions such as these are easier to answer. Unfortunately, causes of test score inconsistency are often not examined by test publishers for a variety of reasons. One reason is studies to explain error variance are expensive to conduct. For the population in general, reliability of many tests is sufficient to make such studies cost prohibitive. Where such information is available in test manuals, it should be studied carefully by persons involved in assessment. To understand how test reliability can be affected, it is necessary to understand the assumptions and practices which underlie test reliability. The following underlying assumptions are extremely important in understanding reliability. We will begin by looking at how variability affects reliability. Variability, as we are using the term here, simply means how different the test scores are from one another. If a test was perfectly reliable, a person who scored 10 on a test last week would score 10 on that same test this week. A person who scored 5 last week would score 5 this week, and so on. A graph of the test scores might look like this. Each dot on the graph indicates one person's score on the 2 administrations of the test. If we draw a horizontal line through a dot, we discover a person's score on the first administration of the test. Drawing a vertical line through the dot tells us the individual's score on the second administration of the test. Here you see a graph of a perfectly reliable test. All of the dots or points in this graph fall along a single straight line. In practice, there are no perfectly reliable tests of human behavior. As noted earlier by Dr. Eldridge, test scores may vary from one administration to the next for a number of reasons. Therefore, you would be more likely to see a graph of test scores that looked like this. Notice that while the points on this graph do not form a straight line like the earlier example, they form a grouping or distribution that generally conforms to the line. Scores on the 2 administrations of the test did not match each other exactly, but were very close. A distribution of scores like the one shown here would indicate a reliable test. That is, a test with a high reliability coefficient. A graph for a test with low reliability would look like this. The points are randomly scattered around the chart. You can see that some people scored higher on the first administration of the test and lower on the second. Other people scored lower on the first administration and higher on the second. And there were some people who scored about the same on the 2 administrations. The point is that there is no discernible pattern in this distribution. These data suggest that this test is not reliable. It has a low reliability coefficient. However, it is possible that the group tested in this example had a constriction of range. This means that the highest score and the lowest score were closer together than the scores you might expect to find in the target population for this test. Here are the scores plotted in this example. You can see that the lowest score is 2 and the highest score is 10. The range for our group is 8. If in the target population, you might expect to find a range of 50, that is, scores ranging from 0 to 50, the chart might look much different. Take a look. Here are the original data on a chart capable of showing the full range of scores. The original data look as if the reliability is quite low. However, when we add in the data for the rest of the population, you can see that this test has reasonable reliability. Constriction of range caused us to underestimate the reliability. Just as constriction of range causes underestimate of reliability, extenuation of range may cause an overestimate of reliability. Take a look at these data. It looks as if this is a reasonably reliable test. Unfortunately, our sample group had a broader range of scores than the target population. Now look at the extended range and the range of the target population. You can see that the extenuation of range gave the appearance of greater reliability than actually exists. Extenuation of range caused us to overestimate the reliability. The variability among test scores affects perceived reliability. In the previous examples, variability was affected by constriction and extenuation of range. As you have just seen, the principle at work here is complicated to explain, but it's easy to state. As score variability decreases, reliability coefficients decrease. And as score variability increases, reliability coefficients increase. This same principle affects test reliability for other reasons as well. Variability among test scores is also affected by the difficulty of the test questions. If the test is too easy, most of the scores will be very high. Conversely, if the test is too difficult, most of the scores will be low. As you saw earlier in the discussion of constriction of range, this may lead to an underestimation of true test reliability. Because of this, test reliability is enhanced when most items on the test are of median difficulty. This may seem strange until we remember that reliability formulas were developed for use with norm reference tests. Norm reference tests are generally used to compare the performance of different individuals or groups of individuals. They are also used to predict some future performance. We will discuss this further in a later module on validity. Another factor affecting the reliability coefficient is test length. When items are of equal reliability, increasing the length of the test will increase the reliability coefficient. In test construction, items are sometimes added specifically to increase test reliability. All things being equal, a 100-item test will be more reliable than a 10-item test. The effect of lengthening a test on test reliability can be predicted using a mathematical formula called the Spearman-Brown formula. Adding items to a test will reach a point of diminishing returns. Adding additional test items beyond this point does little to increase the reliability of the test. The length of test principle explains why subtests or subscores are almost always less reliable than the total test. This principle is important to keep in mind when interpreting tests. Often conclusions about specific strengths and weaknesses are based upon subtest performance. When doing so, the decreased reliability of subtests should be kept in mind. The relationship between length of tests and reliability may be of concern when testing persons with disabilities. This is especially true when physical or health disabilities are present. Scores of tests may be influenced by fatigue factors. A common accommodation is to split the test into 2 or more administrations to reduce the effect of fatigue. When this is done, it should be kept in mind that 2 short tests may not have the same reliability as 1 long test. This principle is also important to consider when tests have both a short form and a long form. The long form of the test will almost always have higher reliability than the short form. Most formulas commonly used in calculating reliability coefficients make assumptions about the nature of the data. Probably the most critical of these assumptions is that the data is linear. Another important assumption is the data is normally distributed or at least is reasonably symmetrical. Worksheets to practice using the reliability principles introduced this far are found in the printed material. Please complete these worksheets now. Turn the video back on when you are ready to continue. one type of reliability. Each type is used for specific situations. The three main types of reliability are test-retest, also known as the coefficient of stability; alternate forms, which is also known as the coefficient of equivalence; and split-half reliability, which is a measure of internal consistency. In test-retest reliability, a test is given, a period of time elapses, and a retest is given. This type of reliability is called the coefficient of stability. It provides an indication of the stability with which the test will measure. If the time elapsed is not so long that the new learning or behavior changes have occurred, or so short that the person remembers previous answers, then the consistency with which the test measures from one testing to another can be estimated. In actual use, if this consistency is high, we can be reasonably sure that any changes in scores are not the result of random error variance within the test. In situations where retesting is mandated, such as special education, this is an important consideration. Alternate forms reliability, which is sometimes called parallel form reliability, can be used when there is more than one equivalent form of the test. This type of reliability involves administering one form of the test, allowing time to elapse, and then administering a second form of the test. Because the two forms are equivalent, retesting with the alternate form serves the same purpose as the retest in test-retest reliability. The question that is answered is slightly different, however. The reliability question answered relates to how comparable the two forms measure. As in test-retest reliability, the time lapse cannot be so long as to allow change in the person. Because the test items are not identical, the time lapse may be shorter than in test-retest reliability. In split-half reliability, a single testing is administered. After administration, the test is divided into two parts, and the scores from the two parts are compared. The test is commonly divided by using odd and even test items. However, the test could be divided in other ways. Split-half reliability is a measure of internal consistency. To the casual observer, it might appear that split-half reliability provides little information of value. The purpose of reliability must be remembered. The focus is to identify the amount of random error variance that occurs during testing. By random error variance, we mean how much variability in scores on the two administrations of the test is due to such random causes as lighting, heating, anxiety, physical fatigue, etc., which supposedly affects all persons nearly equally. Comparing the random error variance of one half of the test with the other half of the test can provide an estimate of random error variance for the total test. So far, we have been talking about test reliability, but there are other measurements that must have reliability considered. Human judgment is often used in the evaluation of persons with disabilities. Observer rating scales, tests that use subjective scoring methods, interviews, adaptive behavior ratings, and personality ratings are just a few examples. With inter-rater reliability, we are concerned with the degree that two or more scores agree. Given the same information, it would be of concern if two vocational rehabilitation counselors reach two radically different conclusions. When judgments are important in determining services or eligibility, there is considerable need for human judgment to be consistent from caseworker to caseworker. Please complete the second set of reliability worksheets. They will help you understand these different types of reliability. Please stop the video now and complete these worksheets. The interpretation of reliability coefficients is of considerable importance. Different purposes require different levels of reliability. While correlations can vary from -1 to +1, reliability coefficients are always positive. Coefficients vary in the range from 0 to +1. For any purpose, a higher reliability coefficient is better. For some purposes, higher reliability is essential. As a general guideline, it is desirable for test reliability coefficients to be 0.9 or above for achievement and aptitude tests. Personality and interest inventories should have reliability coefficients of 0.8 or above. Reliability, as reported in test manuals, is based upon the sample used in the reliability study. When being used in an actual situation, reliability is specific to that situation. Things which influence situational reliability often reside within the individual. Factors such as the client's testing history, motivation, and emotional state commonly influence test results. For persons with disabilities, special consideration must be given to the effects the disability might have on test performance. As the disability becomes more severe, greater care is needed to match the assessment with the situation. If the client has physical disabilities, some items of special concern are the amount of and nature of test item manipulation, length of test, and time limits on the test. Speed tests are particularly inappropriate for persons with physical disabilities. For persons with hearing disabilities, the way instructions are given, how responses are required, and the nature of verbal concepts are particularly important. For persons with visual impairments, the nature of visual discriminations, size of print, time limits, and speed requirements are particularly important. For persons with health disabilities, the length of the test and time limits may be of special concern. In general, when testing persons with disabilities, examiners should be careful about the nature of the tasks, the nature of administration requirements, carefully review the norming sample, and avoid group tests. Many things can change the reliability of a test during a specific administration. Anything that has the potential to change the score a person receives has the potential to change the reliability for that situation. Because evaluations of persons with disabilities often involve accommodations to testing procedures, this point is especially critical. Even when accommodations are not made to testing conditions, persons with disabilities may not match the norming or reliability population. This can cause tests to underpredict the potential of persons with disabilities. Such factors can affect both the interpretation of results and the confidence we can place in test results. How do we know how much we can rely on a test score to be a true representation of an individual? All measurements are subject to error. Even measurements in the so-called exact sciences have error factors. When measuring human traits, error factors are larger because behavior is complex and changeable. Because of this, when interpreting tests, it is important to take into account the potential for measurement error. The standard error of measurement is the standard deviation of the error curve. What this means is that errors, like many other things, tend to occur in such a manner that they fit the normal curve. In the center of the error curve, errors tend to be small, and there are more of them. As the magnitude of error increases, the number of errors decreases. At the extremes of the graph are large errors that rarely occur. The infrequency of these errors is reflected by the graph's proximity to the baseline. If a test has a standard error of 5 points, there is about a 2/3 chance that a person with a test score of 100 would have a true score between 95 and 105. There is approximately a 95% chance the true score will fall between 90 and 110. The standard error of measurement helps us to remember that obtained scores are only estimates of true scores. Because of this, test reports, especially those generated by computers, often include scores in what are known as bands of confidence. Bands of confidence typically plot the obtained score, then adds plus and minus 1 standard error of measurement to create the band. The standard error of measurement can be calculated if we know the reliability of the test. Here is the formula. Standard error equals the square root of 1 minus the reliability coefficient. There are standard error of measurement worksheets in your print package that will help you to become familiar with the concept of standard error and the calculation of standard error. To close this module, here is Dr. Garth Eldridge.
Now, I'd like to end this module with a word of encouragement. We've dealt with some complex subjects in this module. Over the years, I've watched many students struggle with the concepts you are studying now. I want you to understand that we don't expect you to grasp every one of these subjects after a single viewing of the video. We encourage you to work through the problems on the worksheets, study your readings, and review this video as many times as you find helpful.